Yeah, good afternoon, all of you. Before I start, I should thank Dr. Pratish for inviting me and giving me the opportunity to share my research in front of SGET, SGI community. Today, I'll be talking on understanding fluid flow and vein emplacement in the Chitradurga Schist belt, insights from fabric analysis and paleostress determination. Chitradurga Schist belt is well known and well studied Archaeanized greenstone belt, and it is well known for gold mineralization also. And today I am going to share some of the new information that we have obtained during our last 3-4 years research. So it is well known that there can be strong structural control on hydrothermal mineralization, and the mineralization occur in a vein. It could be quartz vein or it could be quartz carbonate veins. In this context, one of the important mineralization, that is gold mineralization, is important, and in this connection, fault action, and which involves the repeated fracturing and sealing of faults, is also important. There are many researches earlier that has been conducted from the vein orientation data in order to quantify the relative stress or the fluid pressure condition that prevailed during the vein emplacement. However, there are a few work which actually quantifies the absolute value of the fluid pressure condition during vein emplacement. So the upper crustal fluid flows are governed by the pre-existing anisotropy. The anisotropy could be the fractures, foliation in rocks, and they can be reactivated under certain state of tectonic stress and fluid pressure conditions. Therefore, it is important to understand the rock fabric, its anisotropy, and its influence on fluid flow. So today, I'm going to present the information about fabric that are developed in the Chitradurga region. I'll talk about the paleostress condition, then I'll talk about the fluid pressure conditions that are analyzed through the 3D Mohs circle analysis, and finally I'll try to comment on the fluid flow mechanism in the upper crustal regime in that region. So before going into the details, let's have fundamental things what is fabric. So fabric is a relative orientation of parts of rock mass. So here you can see that the fabrics that are red rectangular boxes, they are randomly oriented. Now if we compress it, they will have a certain orientation. We call it's a preferred orientation or the preferred fabric. Here I'm showing some of the common planar fabric as well as the linear fabric which we encounter in the field. And coming to the Chitradurga Schist belt, as I told, this is a Archaeanized greenstone belt situated in the Dharwar Craton. More specifically, it is situated in the eastern part of the western Dharwar Craton, and it is it represents a volcanosedimentary assemblages metamorphosed up to greenstone species to lower amphibolite, and is surrounded by peninsular gneiss. And the eastern portion of eastern boundary of this Schist belt marked by thrust zone. This is known as Chitradurga thrust zone. According to some other people, this is a shear zone, and this is the study area on which I will talk in coming 30-40 minutes. On structural point of view, the area has undergone 3 phases of deformation known as D1, D2, D3. And D1, D2 were coaxial with northwest striking axial plane, and that has developed due to the northeast-southwest directed compression, while D3 characterized the general warping, and the superimposition of D3 over D1, D2 structures produced dome basin structure in that region, and that was on account of northwest, southeast to east-west directed compression. So mainly I will talk about the fabric that are developed in the granite as well as the metavolcanic rocks in the region. I will talk about the paleostress conditions that are determined from the brittle structures from the granite, and I will talk about the vein emplacement mechanism from the metavolcanics or the metabasalt in that region. So here I show you some of the field photographs. So this is the massive metavolcanics metabasalts replete with coarse veins of various orientations with various thickness. Here is a close view of these coarse veins. Here you can see that the coarse crystals are going perpendicular to the vein wall, and mostly the veins are identified as syntaxial vein. And here you can see the veins are displaced by another one, and sometimes the vein occur in the in the wing crack, and sometimes the veins are big enough. As you can see, this type of large vein contains a repeated multiple fault plane with prominent striations, and sometimes it contained the chunk of host metabasalt. And here you can see the red dotted lines are the chunk of host metabasalt. And in this type of large coarse vein, as I told, that these type of lineations are also prominent here, marked by the black arrow. And this is the another fault plane, or the fault that is found in the massive metavolcanics, metabasalt. Here the steps on the fault planes are prominent. Now, if you see the orientation of the veins and fracture, you can see mostly they are randomly oriented, but maxima lies in northwest southeast directions. And this diagram shows the rose diagram shows the fault orientations, and I tried to put the sense of movement on this diagram. And if you see the thickness of the veins, it is observed that the northwest southeast oriented veins are much thicker with compared to the other orientations, and the field foliations are also parallel, measured adjacent to the metasedimentary rock lies adjacent to the metavolcanics, and they are in a good agreement with these orientations. Now, coming to the field photographs from the granites, here you see the granites are mostly massive, devoid of field fabric. However, it is massive, but at places, particularly at the lithological contact, it shows some prominent foliations, and this is the orientation of general trend of this foliation found in that region. Although the granite found massive, but it shows very good texture under microscope, starting from the Joan feldspar, which is a remnant of original magmatic texture. It replete with chessboard pattern textures, the coarse grain showing subgrain rotation recrystallizations. Here is the minmacite, the deformation twin in feldspar, and here the last photograph you can see the dynamically recrystallized coarse grains. So it shows that a high temperature deformation texture as well as the medium temperature deformation texture, as we find the minmacite and the deformation twin in feldspar, as well as the low temperature deformation texture. So it is interpreted that the granite is deformed and the deformation texture developed when it's cooled from high temperature to low temperature during its emplacement. Although the granite do not show any prominent field fabric, but it shows some excellent brittle structures such as faults and the fractures of different modes, mode 1, mode 2. Now coming to the fabric analysis in the metabasalt and granite, the metabasalt in the region and the granite as well are found massive, and we use the anisotropy of magnetic susceptibility studies to know the internal fabric in them. So AMS basically involves the induced magnetism in a sample in different direction and the measurement of the induced magnetization in each direction. So basically AMS gives the orientation and the magnitude of the three principal axes of AMS ellipsoid defined by K1, K2, K3, where K1 greater than is equal to K2 greater than is equal to K3. So for the AMS analysis, we need some sample with some specific size. So after collecting oriented block samples from the field that are drilled, and finally the cores are with specific size are extracted, and this is the measuring unit KLY Forest copper bridge. So using this instrument, we normally use the AMS fabric, and I have measured the AMS fabric from the FAL lab from the Department of Geology and Geophysics, IIT Kharagpur. And these are the various parameters, such as the magnetic foliation defined by K1, K2 orientations, the magnetic lineation defined by K1, which is equivalent to the X in strain ellipsoid, and this is the maximum stretching direction. It also gives a shape parameter and degree of anisotropy Pj. Now, these are the location from where the samples are collected, and this is the magnetic foliation, mean foliation. So, and this is the magnetic lineation. So mean orientation of the magnetic foliation is north northwest south southeast oriented, which is parallel to the overall trend of the seas belt. So it is envisaged that these fabric are the consequence of D1 D2 deformation that are developed during northeast southwest directed compression. If you see the Km versus PJ plot, it shows that they are not linearly related. That means the strain must have played an important role for giving the AMS ellipsoid, and the PJ versus T plot shows that AMS is dominant. AMS ellipsoid is dominantly oblate in shape. Now, coming to the granite, these are the locations from where the samples I have collected, and I have divided into three sectors for the sake of the analysis. And this is the magnetic foliation map. And here you can see the K3 pole to the magnetic foliation. So dominantly this is northwest southeast oriented. However, if I show you the fabric or the magnetic foliation sector-wise, then you can see that in sector 1 and sector 3, the fabrics are north northwest south southeast oriented, while in sector 2, the fabrics are northwest southeast oriented. So it is envisaged that in sector 1 and sector 3, the fabrics are reoriented during later deformation. So that's why they are making certain angle with the previous orientations. Now, if we see the magnetic lineation maps, they are plunging due northwest to vertical to southeast. So this type of plunging magnetic lineations are the result of the dome basin structure found in that region. Now, coming to the paleostress analysis in that region, so paleostress analysis is mainly done from the small scale normal fault from the Chitradurga granite. It has done from the fractured microgranitic enclaves from the Chitradurga granite and the elliptical crust from Thalia conglomerate, and from the small scale normal faults recorded from the metabasalt in that region. So these are the faults that are found in the Chitradurga granite, and again, this is the locations from where the samples are collected. The field data are collected, fault slip data are collected. And if you see the mean deep of the fault plane, it is almost 60 degree, while pitch is at an around 45 degree mean. I'm talking about the mean pitch is 45 degree. So it is not the normal fault, it is oblique slip normal fault. So to do the paleostress analysis, we need some, there are some assumptions. So what are these assumptions? The assumptions are the bulk state of stress is uniform and movement of the fault plane are independent of each other. Slip on the fault plane occurs along the direction of the maximum resolved shear stress under a given stress state, and the faults are homogeneous and a part of same tectonic event. So by doing these assumptions, we can do the paleostress analysis, and there are various methods by which the paleostress analysis can be done. So for example, the fault slip inversions. So here the reduced stress tensors are obtained. So in this reduced stress tensor, we have the 4 unknowns value instead of the 6 unknown, and it is represented by phi, which is the stress ratio that is defined by sigma 1 minus sigma 3 by sigma 1 minus sigma 3. So by inversion of the fault data, we reconstruct the orientation and the shape of the stress ellipsoid based on measured fault slip data. So here, I would like to show you the graphical representation. So this is the fault, the diagram I have taken from Hagenfussion book. Here you can see the lineations are marked by the white lines, and one M plane called the movement plane that are drawn parallel to the lineation, perpendicular to the fault plane, and finally that are plotted in the stereonet. So M plane contains the lineation and pole to the fault plane. So the tangent lineation is drawn tangent to that M plane, And if we collect a number of data, if we plot in the stereo net, finally we'll get the tangent lineation diagram, and we can talk about the state of stress condition in that region. So this is the result. I have obtained from the wind tensor. I have used wind tensor program for this analysis. So this is for the all faults collected, the upper one, and the lower rows, it shows the Paleostress result from sector 1, sector 2, and sector 3. All these faults there shows a dominant north northeast south southwest to northwest northeast southwest directed extensional field, and that could be related to late D3 deformation or D3 compression on account of northeast southeast or to east west directed horizontal compression. So I have also tried to establish the stress regime. So following Delvox and Sparned, I can also deduce the stress regime, and it is found the stress regime are pure extensional domain, except the two locations, that is the Z1 and Z9. But other all the maximum locations, what we found that lies in the pure extensional domain. And we have also tried to establish the slip tendency. Here the red lines indicated the high with high slip tendency, so that are again the good agreement with the D3 compression direction, the late D3 compression direction. I have also tried to establish the stress regime in a different way. So for that we have determined the differential stress, and that is found is 76 megapascal, which is greater than 40 but less than 5.7 T. So again, it established all the faults in that region developed in extensional shear mode failure. Now, the paleostress conditions from the fractured microgranite enclaves. So the Chitradurga granite replete with the microgranite enclaves, and some of the microgranite enclaves are fractured, and these fractures are restricted within these microgranite enclaves. Earlier, there are many works which deals with the shape and orientation of this microgranite enclave. But here, I'm going to talk about the determination of stress from the fractured microgranite enclaves. So these are the microgranite enclaves which are fractured, and the fractures are restricted. And this is the orientation, major axis orientation of these enclaves, and this is the mean orientation of the fractures, particularly the restricted fractures. Sorry. Although the fractures are restricted, but there are other fractures which are not restricted. They cut across the enclaves and they penetrate into the host rock, and sometimes it terminates at high angle into the country rocks. And this is the orientations of the fractures. So we have two types of fracture. One is the non-restricted fractures continuous through the pluton, another is restricted within the enclaves. Since the fractures in granite could be the product of the thermal stress or the tectonic stress, so we have performed both to know, okay, which fracture is related to which stress conditions. So coming to the non-restricted fractures, so what I told that they are strictly dipping and shows the cratered orientations and terminates perpendicular or at hard angle to the Pluton boundary, and their orientation change is according to the Pluton boundary. So the thermomechanical modeling could explain their origin in that region. So following Bergbaud and Martel 1999, we have used the thermal mod. We have performed thermal modeling by keeping some assumptions, and here is the result of that thermal modeling. Here you can see the thermal trajectories, thermal stress trajectories are drawn, and that are quite good agreement with the orientation of the fractures, non-restricted fractures. So it is interpreted that these non-restricted fractures could be the result of the thermal fracturing, and they developed when the granite cooled from high temperature to low temperature and at very shallow depth. But what about the restricted fractures? They are also steeply dipping, and their orientation remains same irrespective of the enclave orientations, as you can see here in this diagram. And they are the orientation remain consistent throughout the Pluton boundary. Therefore, the thermal modeling cannot justify their occurrences. So we need some alternate explanation. So we use plane strain model to explain the occurrence of these restricted fractures within that enclaves. So that has been done following Edelman and Rich 1992. So it is assumed that if you have a stiff inclusions that are embedded in an infinite rock mass, so we can equate, following Jaeger et al. 2007, we can equate the state of stress condition within the enclaves and the state of stress condition outside the enclaves. And finally, we can plot the sigma minimum I, that is the internal minimum stress, and versus the maximum stress, maximum remote stress. So here the sigma minimum I is plotted because this is responsible for the fracturing within that microgranite enclave. So as you can see, if you increase the far field stress, it suddenly the tensile domain, the sigma minimum I, that is the internal minimum stress, moves to the tensile regime very fast with compared to the surroundings. As a result, we are getting the tensile fracture within this microgranitoid enclaves. And if we see the orientation of these fracture orientations, they are consistent, as I told, and they are having very steep dip. That means if this is a mode 1 fractures, then the compression will lie in west northwest, east southeast direction. Then the sigma minimum R must lie at horizontal in north northeast to south southeast direction, and which is a very good agreement with the fault slip analysis that I have obtained from the region. The similar result has been obtained from the analysis of fractured clast from the Palea conglomerate. I'm not going into the details here, but we have obtained the same stress conditions, same north west southeast to east west directed D3 compressions. Probably that is the main reason forming the brittle structure in that region. Now, coming to the fault slip analysis of the metabasalt, although we have received very less amount fault in the field, but it shows a northeast southwest directed extension, and the stress regime indicates a transversional to pure strike slip domain, which is again in a good agreement with the sinistral shearing along the Chitradurga shear zone. Now coming to the determination of fluid pressure condition in that region. So that has been done from the vein orientation data. So following Delany et al. 1986, we can say that the conditions for the formation of the reactivated fracture, we have to have very high fluid pressure, and that should exceed the normal stress acting the fault plane. And following Bear et al. 1994 and Jolly and Sanderson 1997, we can use the driving pressure ratio R dash and the phi stress ratio. Here R dash, in the R dash, the fluid pressure is represented with the help of the maximum and the minimum principal stress, and R dash varies from 0 to 1. If it is close to 1, that means the fluid pressure is high. If it is close to 0, the fluid pressure is very low. So following this, we can actually plot the pole to the vein data, and we can easily determine the fluid pressure conditions, the relative fluid pressure conditions. For example, here, when the fluid pressure is very less, it is equivalent to minimum principal stress, we can see the no orientations are susceptible for reactivations. As the fluid pressure increases, the range of orientations that are susceptible for reactivations, they are increasing. And finally, when it exceeds the maximum principal stress, or it's at least greater than sigma 2, the maximum orientation are susceptible for reactivation. As a result, we are getting a girdle distributions. But while when the fluid pressure is less than sigma 2, we are getting a cluster distribution. So from the distribution itself, we can assume, okay, what could be the fluid pressure conditions, and to know in a better way, we can plot this in the lower hemisphere equilibrium projections, and we can draw the the 3D unscaled 3D Moho circle. For example, here, that are the vein data collected from the Gadag region. And now following Joly and Sanderson 1997, we can use the relative position of sigma 1, sigma 2, sigma 3, and we can define the range of orientation of fractures, that is theta, and we can calculate the driving pressure ratio and the stress ratio. Here the driving pressure ratio is found 0.94 and the stress ratio is 0.87. And we can plot it into the 3D Moho circle. And if we plot the range of orientation of fractures, so here we can define the fluid pressure line by joining this 2 theta 2 and 2 theta 3 point, which is actually intersecting on the periphery. And this is the orientations of the fractures that are susceptible for reactivations. So if we assume, okay, this is not a Gödel distribution, but if you assume, okay, this is a cluster distribution. So by assuming this is a cluster distribution, again, we can establish a low fluid pressure condition following the Joly and Sanderson 1997. And here you can see the R dash ratio is 0.07. And the 3D Moho circle construction repeats a very low fluid pressure conditions graphically, and this is the range of orientation of fractures that are susceptible for reactivation at low fluid pressure conditions. So in this study, I have I have tried to quantify the state of stress conditions as well as the fluid pressure conditions. So depth of faulting and fracturing in close vicinity of the study area in the we found that is 2.4 kilometers. So that is actually obtained from the Thalia conglomerate. And by using this, if we determine the sigma 1, so for the normal stress regime, the vertical stress, the overburden pressure is sigma 1, that is at least 63.5 megapascal. And we can also determine that minimum principal compressive stress at crustal depth less than 7 kilometer by using the del sigma, that is the differential stress is equal to 2 tau m. And we can also use the stress ratio to know the intermediate compressive stress and the fluid pressure respectively. And finally, we are able to plot in a scaled Moho circle the position of the fluid pressure line here. So this is the fault plane orientation or the pole to fault plane orientations that are found in that metabasalt. And sorry, this is the vein orientation found in that region, and it shows the Gödel distribution. So as I told, it shows very high fluid pressure condition if it shows the Gödel distribution. And here you can see the fluid pressure line, and these are the range of orientation of fractures that are susceptible for reactivations. So although this is a Gödel distribution, but here we can see a 3 prominent cluster, at least in at least 2 are very prominent, but this is not sure. However, if we do some statistical analysis, let's say the Brigham statistical analysis, it reflects the 3 clusters within this diagram. And if we separate this, let's say for this cluster, which is west-south-west cluster, again, we can get a very low fluid pressure conditions. Similarly, we can do for the other 2 fluid pressure conditions, that is the northeast clusters and the southeast clusters. So we are getting a multiple fluid pressure conditions from high to the low fluid pressure conditions. We have also tried to establish the reactivation tendency in that region. So for that, we have used the dilation tendency, slip tendency, and the fracture susceptibility. So the pole to fractures forming cluster around sigma 3 in both these high fluid pressure conditions and low fluid pressure conditions. So this is a high dilation tendency for the opening, and in case of slip tendency, fractured 2 poles at a low angle to the sigma 3, high slip tendency of the shear opening, and in the fracture susceptibility, it shows the fluid induced the fracture reactivation in that region. So coming to the model here, it is interpreted that during D1, D2 deformations, the northwest southeast or not northwest southeast oriented magnetic foliation developed on account of northeast southwest directed compressions, and this is the mean magnetic foliations. And during D3 deformation or late D3 deformation, the Chitradurga shear zone, they evolve as a sinistral shear zone. As a result, the fractures that are fall or the faults that formed as a part of the radial shear system. And it may be noted that here we are getting dominance of the Y shear, which is again coinciding in the mean magnetic foliation in that region. So since the magnetic foliations lies in these directions, and obviously this direction will be the weaker than the other direction, so that's why we are getting the mode shear, or we can say the mode shear are partitions along this direction. And this is again in a good agreement with the paleostress condition that are established from the false slip data from that metabasalt. Now that stress regime, as I told, that also established from the fractured microgranite enclaves as well as the false slip analysis from the granites. Now in D3 deformations, in that same deformations during high fluid pressure conditions, the fluid burst into the fracture. All the fracture orientations, they are susceptible for reactivations. So we are getting the veins at various orientation, different orientations. So when the fluid came into that vein, it will crystallize and essentially it will create a low fluid pressure condition beneath it. So at this low fluid pressure condition, only north-northwest, south-southeast oriented fractures are susceptible for reactivation because the anisotropy lies in this direction, the magnetic foliation lies in this direction. So in this condition, only the northwest southeast or northwest southeast oriented fractures are susceptible for reactivation. And here, these two fluid pressure conditions, the high fluid pressure condition and the low fluid pressure conditions, are we envisage that probably these conditions have repeated multiple times in number of times. As a result, we are getting the veins in various orientations. So further, we have tried to calculate the port fluid factor following the Mazzarini et al. 2019. So the port fluid factor, it varies from 0.68 to 0.87, which supports the suprahydrostatic fluid pressure condition. Again, in a good agreement with these fluid pressure conditions that are that prevailed in that region. So again, this is supported by this type of field photographs where you can see the chunks of the host rocks that are embedded in that large quartz veins, and these quartz veins also replete with a fault plane. So these fault valve actions with the due to this high or the fluid pressure fluctuations are common in that Chitradurga region. Now, coming to the conclusions, I'd say that the north-northwest, south-southeast oriented magnetic fabric recorded in the metabasalt is a product of the D1, D2 regional deformation. The fabric was favorably oriented and therefore suitable for fracture propagation in relation to the prevailing stress field. Paleostress analysis using false slip data recorded from the study area reveals north-northeast, south-southwest directed extension. The variably oriented fractures and faults are the radial shear components, and the north-northwest, south-southeast to east-northwest, southeast oriented, the P, Y, and R are abundant, owing to their favorable correspond to the pre-existing anisotropy that is defined by AMS studies. And the north-northwest, south-southeast trending orientations having higher values of the sleeve and the dilation tendencies channelize fluid during the both high and low fluid pressure condition, thereby adding the maximum vein thickness in that region. Evidence of fault valve behavior, cyclic fluid ingression, and the fluid-induced fractures fault reactivation have been recorded from the field studies. The vein emplacement took place under both high and low fluid pressure conditions, and it is envisaged that n number of times such alternating high and low fluid pressure cycle prevailed in that region. Intermittent episodes of fluid pressure build-up led to the fluid-induced faulting, rupturing, and vein emplacement in that region. So that was all about my talk. I'd like to acknowledge DSTCRB Early Career Research Award for fund. I'd like to acknowledge Jadavpur University Minor Project, UGC Innovative Project, and RUSA too. I would also thankful to Department of Geological Sciences, Jadavpur University, although I'm shifted recently from Jadavpur to ISI Kolkata, but maximum work has been done from the Department of Geological Sciences, Jadavpur University. I'm also thankful to Geological Survey of India, Bangalore, for providing the logistic support during field work. And I'm very much thankful to my PhD scholar, MSc students, and collaborator. Thank you very much.